Hi there everyone. Today is week 2 of summer school 23 and today's lecture is going to be about dimension reduction. So let's quickly go to the lecture. It's already 8.
My name is Abul Saru. I am a senior manager for applied science at Worldwide Search Amazon. I'll be leading this session on dimensionality reduction, which is one of my favorite topics in machine learning. So the usual approach to building machine learning models, the supervised machine learning models, is to have data, usually lots and lots of data.
Some advanced topic they cover TSNE and KL divergence. So that they discussed, and now it is 14-minute break. Let's skip this ASAP.
Okay, getting ahead with the objectives of this module. So what we are going to do is that we are going to learn a little bit more about dimensionality reduction techniques. In particular, we are going to talk about like singular value decomposition or SVD. We're going to talk about principal component analysis or PCA, and in addition, we are going to talk about matrix factorization. We are also going to talk about a little bit about like where does one apply which particular of these. We will touch very briefly on autoencoders, which are or sort of the representation learning. But representation learning and embeddings and autoencoders, they're a big area in themselves, and I think that's probably a story for another day. But in this module, we will restrict ourselves to SVD, PCA, and matrix factorization as such. So the motivation behind, like sort of like we discussed earlier also, right, that we are deluged with large amounts of data. We can either see this as a challenge or utilize the most of it. So dimensionality reduction techniques, what they do is that they essentially present us with a way of capturing out information from this large data set as such. That's just sort of the recapitulate of what we have learned till now, right? Some of the applications of dimensionality reduction. So, for example, there are recommendation engines that benefit from this. Essentially, when you say that in a movie recommendation problem, for example, the users are sort of a certain number of types, the movies are of a certain number of genres, and that there is an overlap between the types of users and the type of movies. So there is a certain structure of the problem that we can benefit from. Similarly, in genomics, if we were to try and sort of read the whole gene data, probably will get too much. But in case you are able to sort of organize that using dimensionality reduction techniques, it becomes a little bit easier to visualize what exactly is happening, right? And similarly, like sort of for image and voice recognition, for example, in sort of large social networking companies have this problem of being able to like recognize faces, right, and be able to disambiguate if two faces are the same or not, or of the same person or not. So these kinds of like classifiers for image and voice recognition, they sort of tend to utilize a lot of dimensionality reduction. In Amazon also, like sort of for voice recognition on Alexa and a lot of image recognition that we carry out, dimensionality reduction plays a large role. So, for example, for product recommendation, the problem that we are facing is that
we'll
what kind
continue
of
the
recommendations
course.
should be showed. We were able to also discuss like sort of some of the algorithms that exist to solve these. And the current state of the art is that these problems can be solved for very large scales, and they are quite sort of efficient tools that exist out there. My recommendation to you would be experiment them in your next ML model problem that you pick, in the next problem that you try to solve, the next ML hackathon that you attend. Experiment with these, they may be able to give you a substructure that is much easier to solve. Many of these, like the matrix factorization solution to recommendation systems, is actually the state of the art for giving movie recommendations, right? And just to sort of revise what we have learned, like sort of in terms of the conceptual items that we went through, PCA is your singular value decomposition of a centered matrix. Centered matrix, what you have done is that you have just taken the row of the X matrix and sort of subtracted the mean out of that. Your matrix factorization is the composition of an incomplete matrix where the individual elements are not completely observed. There is another like sort of decomposition. Tensor decomposition is when you have higher order matrices involved or tensors involved. And my overall recommendation would be that sort of please revise your linear algebra 101 again. It is probably more useful than what you thought when you first studied it. Thank you so much for your attention.
So are there any books for mathematics for deep learning and data science? I think there is one. I think it's called Mathematics for Machine Learning itself. It shouldn't be read as a simple textbook. It should be read as a reference textbook one thing. So when you're coming across as these terms, try to work at it from a top-down approach rather than a bottom-up approach, because the bottom is quite huge. So there are a lot of different things that you can think about. If you start working from the bottom, you'll try to go into aspects which are not really useful for you. But working from a top-down approach, at least because the field has expanded so much, it'll be easier for you to grasp this aspect. And then once you reach the tail end of it, you can start exploring more. So it's kind of useful for that. But in a research sense, that is what my take is. Prince, do you have anything else to say to this?
No, Asudos, I think you have already covered in good details. So.
Okay, sir, when we have vector embeddings for documents and while clustering those embeddings, is dimensionality reduction a good way to proceed? If yes, which are the good ways to reduce number of dimensions? I think Prince can take this question.
Yeah, I think when we have embeddings, so I think I mean you might not want to reduce dimensionality of those embeddings directly, but I mean one case where dimensionality reduction happens in a sense is where you have those documents containing terms, and then you try to reduce that to a certain set of embeddings. So that's where you already reduce the dimensions and map them to a representation space that is meaningful. Beyond that, I mean, it really depends if you want to do it, or if that itself gives you good performance, then you can keep at that. So that's what I can think of here.
Right. Yeah, I think I also don't have much to add to this. When we have vector embeddings for documents and when clustering those embeddings is dimensionality reduction a good way to proceed, you can directly use clustering on it. But as again, I think we talked about this earlier, it becomes difficult in higher dimension to cluster because clustering uses some form of distance measures as well. If you can work with distance measures which are not Euclidean, so there are these different kind of Poincaré embeddings, Poincaré distance and so on that you can work with. I mean, I'm just digressing, these are not part of these, but there are different ways of measuring distances as well. If you're able to work with those different distances or metrics metric spaces that are called in mathematics, if you're able to work with that, then that would be, I think, better. So TSNE and all helps you in visualizing those better, but it's usually if you start working on a high dimension cluster, those vector embeddings, that should suffice, because I think you are working with document vector embeddings of fixed sizes, I'm assuming, unless and until you're working with large language model where each of the token has a different representation. So yeah, I think that's probably it. Is there a good way to reduce the number of dimensions? Yeah, I mean, there can be, but you wouldn't kind of want to do it. You would want the model or deep learning model to do that for you, because we're talking about vector embeddings. I'm hoping we're working with deep learning models itself. How does gradient descent optimize? I think we've answered this already. I think this brings us to the end of the questions. If people have more questions, they can ask. We have some time.
Yeah, do feel free to ask any questions in general, about any topic that you might have. We'll try our best to answer. We still have some 10 minutes. So
now, in the higher dimensional representation, far and close are not very interpretable in the terms that a far distance in a higher dimensional space does not necessarily mean that a far distance in a lower dimension space does not necessarily mean a far distance in a higher dimension space, and vice versa. So the main constraint there is up to a certain limit, you can have these nuances if you measure in terms of Euclidean distances. But if you have a higher separation between 2 points, higher separation between 2 points, as has been seen algebraically, is kind of equal to having 2 points which are very close to each other. So both of them kind of reduce to the same level. That's where it's not very feasible to do this. I think that's where, and also we wanted to do like these T students stochastic neighborhood embedding, which we wanted to do in the lower dimensional space as compared to a higher dimensional space because of the long tail that happens in the lower dimension. That's what we are trying to incorporate there. We aren't working with the original objective, we're working with the objective which has a modeling of normal distribution in a higher dimensional space and Gaussian distribution in a higher dimensional space and T distribution, T student distribution in a lower dimensional space. That's what my interpretation of this question is. So if there's any follow-up to this, let me know.
So Ashutosh, I believe we have a few new questions. We can.
Okay. I think there are a lot of questions. Prince, can you start? I lost track of where I was.
Okay. Yeah, I think let's start from the new one. So the first is any real-time suggestions for dimensionality reduction in real-time scenarios. I think again real-time scenarios, allude to the point that you have certain constraints on your latency. So I mean in general, right? You want to do dimensionality reduction there, or in general, reduce your model size so that you can improve on your latency for your requirements. Any suggestion as such? I believe you could try out, different techniques that were discussed and then see which one works well. So I think we have discussed most of these techniques in details already. So yeah, I believe that's all.
Mathematical basics that are required, but the calculation is very intensive. So that's the thing. I mean, it's not that you need to understand all of the basics. It's just one level of basics that you need to understand. So I think there it's useful. Though I have good knowledge of statistics and linear algebra, when I go through research papers on GAN, there are some terms like K11 and JNST which I'm not aware. Okay. The good thing that if you do through advanced degree is you're hoping to become specialized in one of the fields, which is kind of a depth first approach in an industry based setup, or if you're working in general ML problems, you know how to work with different problems, because I have seen in fact myself struggling with problems if I've been given from a very diverse perspective. If it's very nuanced to some things that I've already worked with, it becomes easier for me. So I mean, this question does not have a yes or no answer. Again, it lies somewhere between 0 and 1. So yeah, Prince, do you have anything to add to this?
No, I think let's move on in the interest of time.
Okay, what all to read MariaNMT model for text translation? Is there any other better way? Yeah, I think there are a lot of different models. This MariaNMT is just one of them. You can use for translation. You can directly use off-the-shelf large language models now. They work well as well. Please playlist on YouTube for LA. Please suggest a playlist on YouTube for linear algebra. I can't think of, but it's better to. I mean, that's a very biased perspective, but it's better to start with the books. I think Khan Academy also has a good set of lectures on linear algebra. In bagging, is there a condition where sample size and it should be the same as the size of the input data? Prince, would you like to take this?
Yeah, and so in bagging, is there a condition that the size of sample in every instance should be same as the size of the input data? I think it would also depend on the model that you're using for bagging. So bagging is where you have a certain data set and then you train multiple models with different either initializations or different sets of features. So generally what I've seen is, for any given model in that set of models, it's best to have, the same features present in all of your data, because you don't know that, which feature might be important, which may not be. But then across different models, you could, remove certain features or remove certain data points. So all of that is doable, is possible.
Yeah, so in brief, there's no strict condition here. You can work with different dimensions of the dataset points as well as features. So when I use CNN model, sometimes I get error in size of input is not compatible. Oh, I think Google would be better person to answer that. There are a lot of different forums where you can look at. I think if you use the standard libraries, it might be better to work with that. Otherwise, the most generic suggestion that I can give you is just see that your padding is the same for all the images that you're working with. How to decide the momentum value best for our work? Optimization question. Prince, would you like to take this?
Yeah, momentum, I guess. I mean, there's no, I mean, you could do like hyperparameter tuning of that, but generally what I've seen is
momentum-based gradient methods or Nesterov gradient methods, then you really need to tweak that. But if you're working with Atom, Adafactor, those kind of are inherent in the objective function or the update itself. So it updates for you directly on not only first order but second order differentials as well. So I think it'll be easier to use Atom in those perspectives. Is it important to learn mathematical interpretation of algorithms? Depends on what level of details that you want to go. If you're researching and you want to see if those mathematical aspects might help in improving the algorithm better, then definitely. Otherwise, if you're just working with the algorithm, then and the different cases where you need to figure out, given this input, what is the output and what are the constraints that we need to satisfy in terms of budgets, then you need to really know the algorithm better as compared to the mathematical interpretation of it. If you're researching, it's better to do this. I think subjective question again. So, Prince, do you have anything to add to this?
No, I suppose I think let's move on given the...
Okay. Some online resources to learn more about dimensionality reduction. I think there might be plenty, but at least whatever has been presented in this talk is quite sufficient for you to get started, and then just search those topics and then you'll be able to find a plethora of them individually. But this gives an overview, good overview, broad perspective of whatever happens in dimensionality reduction. How do I handle categorical variables in dimensionality? Can you describe a specific approach? I think mutual information does that for you. So just if you have tabular data and you're working with categorical variables, use the mutual information metric as compared to Pearson correlation in that case. Okay, again, the same question. Okay, I think that brings us to the end of the questions. Yeah, I think Soumya, you can take over. Is Soumya here?
All right. Thank you so much, everyone. I think that was a great learning experience. I hope all of your questions got answered. We'll see you in the coming sessions. Tomorrow we have the next session coming up on unsupervised learning. So I hope all of you have registered, and see you in the coming sessions. Thank you.
Thank you. Bye-bye.
Thanks, everyone. Have a good day.